Chapter 5, Inference for Numerical, which is quantitative data. In this activity, we're going to look at quantitative situations where we use numerical data to calculate the mean, and we're going to look at how we can make statistical decisions based on the data that we're looking at. So we'll continue with hypothesis testing like we did in Chapter 4. Pause the video and read why learning objectives and vocabulary if you have not already. Example 1 is a vocabulary check. In a matched pairs experiment, subjects push a button as quickly as they could after taking a caffeine pill and also after taking a placebo pill. So in a matched pairs, it's where we compare typically someone to themselves. Sometimes if you have twins, you could do a matched pair study with twins. Here, the first group would be the person after taking the caffeine pill, and the second group would be that same person after taking the placebo pill. So we're comparing people to themselves. That's called the match of the matched pairs. The mean pushes per minute were 283 for the placebo and 311 for the caffeine. Is each of the bold numbers a parameter or a statistic? Since both values are from an experiment, we assume this is a sample, so these are statistics. Question B. The Bureau of Labor Statistics announced that last month it interviews all members of the labor force in a sample of 60,000 households. 8.9% of the people interviewed are unemployed. So the bold font number here, that 8.9%, is a statistic because it came from the sample of 60,000 households. Question C. A study of voting chose 663 registered voters at random shortly after an election. Of these, 72% said they'd voted in the election. Election records show that only 56% of registered voters voted in the election. So this bold font number, the 56%, is a parameter because it's all of the registered voters. So sometimes in voting scenarios where we're counting every vote, we do have population data. Question D is about scores on the mathematics part of the SAT exam. So we're told that they were roughly normal, the standard deviation is 114, and you're choosing a simple random sample. So note SRS is just shorthand for simple random sample. So what's going to happen to the mean if you choose very many simple random samples? Well, remember, we expect the mean should stay the same. Think back to the NBA salary sampling applet that we did. And remember, the mean didn't move. The distribution itself became more compressed when we were sampling, but the mean stays the same. So the mean should stay at 515. So if you imagine a normal distribution for the sampling distribution here, it should be centered at 515. E is now that same scenario, but now they're saying what's going to happen to the standard deviation of the average scores if we do a sampling distribution. So we know in a sampling distribution, the distribution shrinks or becomes compressed. So if you look at answer choice C, that's following our formula, sigma. The standard deviation is 114 divided by the square root of n, where n is 100. Question F is about a light bulb. And we're told that the distribution of the burnout times is strongly skewed to the right, meaning a few light bulbs last a long time, but most light bulbs burn around the average amount. So the central limit theorem says what? Well, answer choice C is the most clear explanation of the central limit theorem. It's telling us the average burnout time of a large number of bulbs has a distribution that is close to normal, and then I added it's also going to be centered at the mean. Example 2, we're thinking about how we apply the law of large numbers. So remember back from Chapter 4, according to the law of large numbers, if we keep on taking larger and larger samples, the statistic x bar, that's our sample mean, is guaranteed to get closer and closer to the population parameter mu. So that's our population mean. If we are able to keep measuring more subjects, eventually we will estimate the mean value very accurately. So question A tells us there are twice as many slot machines as bank ATMs in the US. And we're told that the gambling houses have around 5% profit, and a friend who knows you are taking a statistics class text messages you that she just won $100 at a slot machine in Reno. So should your friend spend her $100 playing more slot machines? So I say the best advice to text back is to tell your friend to stop gambling. You are ahead if you just won $100. In the long run, you will lose 5% to the gambling house. If you gamble that $100, you will likely only win back around $95, right? That's a 5% loss. Question B asks about this idea of insurance. So an insurance company is looking at the records for millions of homeowners, and they see that the average or mean loss from a fire per year is $250 per person or per home. And that's because most homes have no loss, but there are a few homes lost. So this $250 is the mean or the average loss. So the company plans to sell fire insurance for $250 plus enough to cover its costs and profit. So we want to explain why it would be unwise to sell only 12 policies. So if one house burns down, 12 times $250 is $3,000 total that the company is going to take in from selling these policies. So this is not enough to cover one house burning down. However, thousands of policies should cover the cost of one or a few houses burning down. So to spread out the loss, the company needs to sell many thousands of policies. So we're going to see now when we set up our hypothesis test, since we're working with quantitative data, the claims are going to be statements about the population mean. Later on, we'll see that the claims can be also statements about the population proportion when we're working with categorical data. So let's look at a hypothesis test with one mean. So take a minute and read through the paragraphs here. We're told that the mean height of young men for the population is 69.5 inches, and the standard deviation for the population is 2.8 inches. And you're conducting a survey to measure the heights of 250 male students at LMC, and your sample mean is 70 inches. So you think the mean height of male students at LMC is going to be greater than the mean height of all young men. So you are going to set up a hypothesis test. So remember, the null hypothesis, H sub 0 says no change. So in this case, we write mu equals 69.5 inches. So here I'm using symbols to write out my hypothesis. You could also write sentences to explain. So this mu equals 69.5 inches is saying there's no change from the population mean. Our claim is that LMC young men are taller than that average. So our alternative hypothesis is that the mean is greater than 69.5 inches. So now we want to record the data. So our mean was given, our population standard deviation was given, our sample mean was given. We know we're sampling, so we want to think about, well, what would the standard deviation of the sample distribution average be? And so we take our 2.8 and divide it by the square root of 250 because there were 250 men in the study, and we get the sampling distribution standard deviation should be 0.177 inches. Because remember, we're pulling out 250 men and taking their average, and if we do this many, many times, we're going to get that sampling distribution graph that's going to have a center at 69.5 and a standard deviation 0.177 because it's an average of 250 men, so it's not going to have much spread. So now let's go into StatCrunch. And we're going to go to Stat, Z Stats. This is one sample because we're just looking at one group. And then we're going to say with summary. With data would be if we had a whole data file behind us. So our sample mean was 70 inches. The standard deviation, if we look back, is 2.8 inches. Our sample size is 250 young men. And then we're comparing it to the population mean that's the 69.5. Now what's really great about StatCrunch is as soon as I type in the 69.5 here, notice it auto fills it in for the alternative hypothesis because you have to have the same value here. So StatCrunch is making sure you can't make any mistake and put different values in here. Since our claim is that the mean height for LMC young men is greater than this, we use the greater than inequality. And notice I've got the hypothesis test bubble checked here. If you wanted to do a confidence interval, you could check this bubble and set your confidence level. And then I like to see the p-value plot, so I'm going to check that off and compute. So here is where I'm getting the z-stat. You could certainly work it by hand using the z-score formula, and you could find the p-value by hand using the p-value z-table on page 129 to 130, but it's much faster to let software do this for us. And you can see our standard error here matches what we calculated, sigma divided by square root of n. And if we come over to the p-value plot, we see here we are more than 2 standard deviations away. Our p-value is quite small, so this is looking like there is evidence to support the claim. So we record our z-stat and our p-value here. We note that our p-value is less than our significance level, 0.05. Remember, if I don't state the significance level, we assume by default that we're working with alpha equals 0.05 or a 5% significance level. So our conclusion is that we reject the null hypothesis. The average height of male students at LMC is statistically significantly greater than 69.5 inches. It would be unusual to have an average height of 70 inches from a sample of 250 male students if the population average was 69.5 inches. So remember, our hypotheses are competing claims. So when we reject the null hypothesis, another way of saying this is you could say we support the alternative hypothesis or we support the claim. So let's look at what happens if we have two means. So in this description, you're told about the book Garbology, our dirty love affair with trash, and a researcher is trying to figure out if synthetic polyester fabric decays significantly different than natural fabric. And so the researcher buried 120 strips of polyester fabric and 140 strips of cotton fabric in a landfill for 6 months. So then after that, they came back and found the mean amount of polyester fabric remaining was 0.92, and according to fabric manufacturers, the standard deviation for all polyester fabric is 0.30. And the mean amount of all cotton fabric remaining was 0.87, and according to fabric manufacturers, the standard deviation for all cotton fabric is 0.43. So we want to set up a hypothesis test for this claim. So since we've got two groups here, or two populations, the polyester fabric and the cotton fabric, we say this is a two-sample hypothesis test. Since we know the population standard deviations, we are able to use the z-test. So when we have two populations, you have to first define which mean is which. So I'm going to say here mean 1 is the polyester mean remaining fabric and mean 2 is the cotton mean remaining fabric. It would be just fine if you did it the other way around. Just make sure your inequality goes in the proper direction. So the null hypothesis is equality. We're assuming there's no difference between the two fabric types. So we have mu1 equals mu2 for the null hypothesis. And for the alternative hypothesis, because it said the researcher wants to know if they decay significantly different, we use the not equal to inequality because the claim is about the two fabric types being different. So we want to collect or record the data. In this case, the data is given to us. So polyester had sample mean 1 of 0.92, N1 was 120, and sigma 1 was 0.30. So when we're working with two groups, we put these subscript 1s on all of the variables here for the first group, and then subscript 2 on all the variables for the second group. So you can see the cotton sample mean from the paragraph was 0.87, and 2 is 140 because there were 140 cotton strips, and sigma 2, the standard deviation for the cotton population, is 0.43. So let's head over to StatCrunch and run this hypothesis test. So we'll exit out of our previous hypothesis test. We go to stat. We choose z-stats again because we have information about the population standard deviation. And now we're going to choose two sample with summary because we've got the summary data. So we look back, sample mean 1 was 0.92. The sample mean 1 standard deviation was 0.30, and there were 120 values in the sample 1. And then if we go to sample 2, the sample mean was 0.87. There were 140 values, and the population standard deviation was 0.43. And now our hypothesis test, when we have it set up in StatCrunch, the way they do it is instead of saying mean 1 equals mean 2, they say mean 1 minus mean 2 is 0. That's the same thing as saying equality. So we're just always going to leave this at a 0 here. We're not going to try to figure out if the difference is some other number. And then we want to make sure our inequality matches our claim. And so here our inequality was that there's a difference, so we choose not equal to here. And then I like to see the p-value plot, so I'm going to highlight that here and press compute. So this first screen gives me the z-stat and the p-value. So I see the p-value is higher than our significance level, and the z-stat is less than 2 standard deviations. If we come look at the p-value plot, we can see this is two-sided because we use the not equal to inequality. So we could be greater than or we could be less than in our relationship. So we record those values in step 3. I noted that this is greater than the alpha is 0.05 significance level. So in this case, because we are not getting unusual results, we fail to reject the null hypothesis. We say there is not a statistically significant difference between the sample means of polyester and cotton fabric. It is possible that the average decay is the same for polyester and cotton fabric. So now, what happens if we don't know data about the population? In real life, we often don't know the population standard deviation sigma. So we use a model for the sampling distribution. And this model is known as the T model or the T distribution. So it's similar in shape to the normal distribution, but if the sample size is less than 30 subjects, the T distribution is a little bit wider on the tails to make up for the fact that the distribution has less data. So here is, if you've got a sample size of 15, here's a normal distribution side by side with a T distribution. And you can see the shape is very, very similar. You see here the tails for the normal distribution has 5% area at this cutoff, and you can see the T distribution is a little bit more area in the tails here. It has 7.4%. And so that's to account in part for the fact that the sample size is less than 30 subjects. If you get n equals 30 or greater, the normal distribution and the T distribution are pretty close matches in their shape. So the normal distribution stays the same shape, but the T distribution shifts a little bit. Let me show you in StatCrunch. If you go to stat calculators, remember we had the normal calculator, you can also go to the T calculator and see how right now the T calculator has, we call it 10 degrees of freedom. If I change that to 15, you can see the shape changes a little bit. If we go to 18, it changes a little bit. It's kind of hard to see here. So maybe we'll put, what if it's, where has it got 0.05? So here it is, if it's got 18 degrees of freedom, our x value would be negative 1.73. And then if we went down to 10 degrees of freedom, see how it changes. We want it when it's 0.05 exactly. It changes a little bit further out. So it's hard to see in the naked eye, but the T distribution does change a little bit, but it still has that basic normal shape. So let's look at an example with one sample using the t-test. So example 5 tells us students in an LMC statistics class conducted a research survey to find if people carried more than 50 cents in their pockets. The students surveyed 125 people and as close to a random sample as possible. The sample mean was 53 cents and the sample standard deviation was 0.275. So we want to test the student's claim to find out if there is actually significantly more than 50 cents in people's pockets. So this is one sample since we're comparing one group to this number value 50 cents. We're not comparing two groups. So we say here when we set up our hypothesis, the null hypothesis is that the mean is 50 cents and the alternative hypothesis is that the mean is greater than or more than 50 cents. So we've got sample data. Now notice, since our standard deviation is a sample standard deviation, I'm using S here, not sigma. That S tells me that this data comes from a sample. So let's go into StatCrunch and calculate using a t-distribution. So we go to stat, and then instead of z-stats, we choose t-stats with one sample with the summary. And our sample mean here was 53 cents. Our sample standard deviation was 0.275, and we had 125 people in this survey. And then we're comparing our mean to 50 cents, so we can put 0.50 here, and we can change our inequality to be greater than, and we can choose the p-value plot and compute. So our t-stat is within 2 standard deviations, and our p-value is above the significance level. And if we come look at the t-distribution, we can see it looks very similar to the normal distribution, and we are within 2 standard deviations. So let's go think about our conclusion. Since our p-value is greater than the 0.05 significance level, we failed to reject the null hypothesis. The mean amount of change in pockets is not statistically significantly higher than 50 cents. It is possible that people carry an average of 50 cents in their pocket. So now let's look at what if we have 2 samples, but we don't know the population standard deviation. In these conditions, we can do a 2-sample t-test. So here is data from a medical study. And notice these are small samples. So we couldn't use a normal distribution here because we have less than 30 subjects. But we could use the t-distribution. It's okay to use a t-distribution with small samples. Remember, the t-distribution adjusts its shape depending on the sample size. So a random sample was chosen, so our condition is met. We've got a random sample. That's all we need to use a t-test. And then the 2 groups here are not obese and obese subjects, and they are measuring their activity levels. So they are measuring, I think, the mean energy spent. So here's the sample standard deviation, here's the sample mean, and here is our sample sizes. So I'm going to say group 1 is a not obese group because they are the first group, and we're measuring the mean minutes per day of activity. That's how they're measuring the energy spent. And then mu2, because it comes second, is going to be the obese mean. So our null hypothesis, which is no change, says that mean 1 equals mean 2. And our alternative hypothesis, because we're saying that we think the not obese group expends more energy, is going to be that mean 1 is greater than mean 2. Our data's all right here, so I just drew an arrow instead of recopying it. And then we're going to go enter this in StatCrunch. So over here in StatCrunch, we go to Stat, T-Stats, 2 samples now with summary. And then I got to look back to remember these numbers. So mean 1, sample mean 1 is 525.751. Sample standard deviation for group 1 is 107.121. And then this had a sample size of 9, I believe. So now if we look back at group 2, the mean minutes of activity per day were 373.269. The sample standard deviation is 67.498. And this had a sample size of 11. So our hypotheses here, we're saying, is the first group exercising at a significantly greater amount of minutes per day. And then we check off that we'd like to see the p-value plot and compute. So here our p-value is very small, and we are more than 2 standard deviations away from the center. So if we look at the p-value plot, we see here's our area way out here, and you can see there's hardly any red, which corresponds with our very small p-value area there. So our p-value is less than the significance level, so our conclusion is that we reject the null hypothesis. The average minutes per day of activity is significantly greater for the not obese group. It would be unusual to have results like this if the average minutes per day of activity were equal